So he's looking at Einstein's solutions. He uses a change of coordinate system, and he finds a model where the radius varies hyperbolically with time, again, the way Friedman models does. But he doesn't know about Friedman's solutions. He says it's inspired by a paper by Weil. Weil also was working on these things quite a lot back then. It's not giving up, as I say, your static monocle in the physical sense, but it transforms this de Sitter line element that de Sitter was using for his solutions, and he makes it sort of non-static in a sense, but it's still a static model, but it has some non-static properties in the same way de Sitter model. It's just to show that other people are also working on solutions to Einstein's equations that you may not have heard of before back in the 1920s. Okay, finally, somebody know Edwin Hubble. Keep an eye on Edwin. I got as many pictures as I could with him with different pipes and different postures. He looks great with a pipe in his mouth. October 1923, he finds a Cepheid, these distance indicator stars, in the Andromeda Nebula. This is a copy of the plate, where he originally thought it was an N star, then he realized later that it's a variable star, so he crosses out the N and writes variable. He used a 100-inch hooker, which was the biggest telescope in the world at that time, and would be the biggest until the Palomar Observatory was built. First Cepheid variable found in the spiral nebula, so he can get the distance to this beast. Finally, we can get the distance to one of these strange spiral nebulae with these high radial velocities. This one's coming towards us at 300 kilometers per second, which is strange, but now we can kind of disentangle, hopefully, what's going on. He publishes a distance, 1925, of 300 kiloparsecs, about 1 million light years. Just to give you an idea of the scale, if this was the actual number is more like 800 kiloparsecs, but not bad for 1925. Small Magellan Cloud is about 60 kiloparsecs. Milky Way is about 30 kiloparsecs in diameter. But the reality is that he pretty much establishes that spiral nebula are external galaxies with these first observations of Cepheids in external galaxies. So, we really didn't realize there were galaxies even outside our own. We didn't realize there was a universe outside the Milky Way until 1925. Of course, supporting Kant's idea of island universes, partial resolution of the Shapley-Curtis debate, it's big news. The only sticking point is this guy Van Manen, who's also at Palomar Observatory, or it wasn't Palomar back then, but at the observatory with Hubble. And Van Manen had been looking at pictures of spiral nebula taken several years apart, and he claimed he could see them rotating in time over several years in his photographic plates. And he said, there's no way this object can be that far away, and I can see this rotation because that would be superluminal light speeds. So this stuck in Hubble's craw for a long time, and it took another 15 years till he was completely done away with, basically. People went back and looked at his data again and realized the guy had hallucinations or something, and he wasn't seeing any such thing. But it took a while for it to become truly established. Okay, so now that we know there is an external universe, what about these large radial velocities? How are they going to fit in now? So we see these objects traveling quite far away, but what's up with these radial velocities that we're finding? So this guy, Knut Lundmark, he's a Swedish astronomer, also a great observational astronomer. He was puzzled by these Silberstein derivations of the globular clusters where he kind of fit the data himself. He says, no way, these globular clusters I think are too close. And he doesn't find any correlation between the radial velocity and the distance when he uses a full sample, which nobody else did either, of course. But he's a really thorough astronomer, so he says, well, let's just test all the different possibilities. He tests this velocity-distance relationship that Silberstein and others have been talking about with Cepheids, with novae, O-stars, eclipses, everything he can find. And then he finally gets down to spiral nebulae. He plots up the 33 nebulae he has radial velocities for, and, well, I say distances, but really we can just say magnitudes because he didn't have really good distances to them. But he refuses to fit a line with the data. I want you to think about how many papers you see published in Phys Rev where they publish a data set and they don't fit a line to it. Not many. He says there may be a relationship between the two quantities, although not a very definite one. 1924, this is the plot. I like this plot for several reasons. First of all, it's the only plot I've seen where someone uses distances of the Andromeda Nebula for his x-axis. And back in those days, you could actually write in the proofs at the last minute that I forgot to put kilometers per second in this. Could you write it in for me? So, first published radial velocity versus distance diagram with no line through it. Okay. Well, I took the data points, I plotted the line for fun. I thought, well, he didn't do it, but why don't we do it anyway, just for fun? If you do it and you fix the axis at 0, and you do least squares, you get a Hubble constant of about 45. Which, if you know what the Hubble constant today is, that's pretty good. And we'll see that number, again, we've had now one estimate of the universe being about 10 billion years old. Here's one with a Hubble constant of about 45. Those are pretty close to modern numbers. But this plot is wrong for several reasons, and he knew the data wasn't very good, so that's why he didn't fit this line. So I wouldn't read too much into that, but a lot of other astronomers would have fit this line, and they probably would have become famous in the long run, because people would have found this and said, hey, look, he had the Hubble constant way back in, but all the wrong numbers. Okay, Beertz and Stromberg, this guy Beertz I mentioned before, he also uses data like that of Lundmark, and he claims there's a log diameter distance versus velocity relationship. So he looks at the diameter of these objects and says, I can get the diameters of these, and of course, the diameters of all these spiral nebulae are exactly the same. They're just, if they're different, it's because they're at different distances. Of course, now we know that's not true. But he came up with some kind of relationship here. This guy Stromberg, who was also at Mount Wilson back in 1925, he uses, again, magnitudes for proxy for distance. And he says the same thing that Lundmark. He says, well, no sufficient reason to believe there exists any dependence of radial motion upon distance from the sun. And he doesn't plot up the spiral nebula one, but he plots up the globular cluster one, and he goes, look, I can fit at least squares for these data points any way you want. There's nothing going on here. So instead of plotting no lines, this suite plots 2 lines to show you how worthless it is. Okay, then it comes along this Belgian guy, Georges Lemaitre, and he's discussing a kind of a non-static de Sitter world, in a sense. So he tries to link this to current observations in a solution that's akin to de Sitter's, and he says, of course, our treatment evidence is this non-static character of the de Sitter world. Remember I said these points that are put in this empty universe kind of move around, which gives a possible interpretation of the main receding motion of spiral nebula. Again, making a direct connection between those observations and the theory as they know it at that time. But no mention of Friedman in this work, because again, Friedman's papers have dropped off the edge of the world. Lanzos, he doesn't know about his papers, or this guy Weil, who also has done some work in this field. Unlike Silverstein's previous work, his treatment only contains redshifts and no discussion of, again, as I said, a Friedman-like expanding universe. This, again, is a de Sitter solution. But he keeps working on it. This guy's a brilliant mathematician. He had worked with Arthur Eddington and had actually been at MIT for a year before this. By 27, though, he independently derives Friedman's equations with the time-dependent radius of the universe. And he showed that these cosmological equations could be satisfied by an expanding universe, and this is the important quote, the velocity of recession is the apparent Doppler effect due to the variation of the radius of the universe. So he's saying these radial velocities you see, these positive radial velocities, are related to the expansion of the universe. He's the first one to make that direct connection back in 1927. And I say a very different understanding of Friedman. I say that because this guy is an astronomer. He understands data. He's been to Mount Wilson. He knows the observations really well. How do I know that? I'm going to show you. So, he derives the distance versus velocity, radial velocity relationship from the data at hand for the spiral nebula using the data of Schleifer and Stromberg and Hubble. Using 42 galaxies that he thought were good enough for the data, he found 2 different values, one by grouping the galaxies in one way and one by not grouping them at all, with a Hubble constant of 625 and in one other case 575 kilometers per second per megaparsec, quite far off from the number we know today. And he cites these previous attempts by Lundmark and Stromberg. But in 1927, he publishes these numbers in a paper. Unfortunately, he published these numbers in an unknown journal called the Analyse Scientifique Bruxelles, that no one read. He sent the paper to Einstein, and Einstein said, you might be right, but I find your description of the universe abominable. I don't like it. Papers are forgotten by nearly everyone again, just like with Friedman's, including Eddington, who he had sent the paper to, who had been his mentor. It was later republished in monthly notices in 1931, thanks to Eddington, because he had been at a conference with Eddington and de Sitter and some other people, and he'd overheard them talking about the possibility of non-static solutions. And he said, I sent you a paper on this a couple years ago, don't you remember it? And Eddington embarrassingly said, no, I don't remember it. Can you send it to me again? He does, and he has it published in monthly notices, but without the Hubble constant calculated numbers. So those two numbers I showed you before didn't show up in the monthly notices paper. This is the paper that was published in that Belgian journal, and I just want to show you here, he calculates 625 kilometers per second per megaparsec, and down here 575 kilometers per second per megaparsec. I have to tell you, it's still hard to get this journal. I had to write a Belgian friend who lives in Canada, who wrote a Belgian friend in Belgium to actually go to the library in Leuven to make a photocopy of it, which was then sent to me. So this journal is really hard to get. So you can imagine how hard. But these pages were missing. So no one knew that this guy had actually calculated what we know as the Hubble constant today, based on those solutions to Einstein's general relativity equations and knowing the radial velocity data and distance data as he did. 1927. Okay, Edwin Hubble 2 years later more or less does the same thing. He uses distances to 24 nebula. He cites Lundmark's work. Of course, he doesn't know anything about the work because it hasn't been published in monthly notices yet. It's in this obscure journal. He doesn't know anything about Friedman's stuff. He doesn't know anything about theory, essentially. In 31, he increases the accuracy of that relationship with 40 more, and the debate more or less ends here on this linear relationship. Einstein at this point abandons the cosmological constant because he says, well, it looks like the data says the universe is expanding. But does Hubble actually believe in an expanding universe? Actually, he's never been quoted of actually believing that there's an expanding universe. And that's fair, because Hubble doesn't know much about the theory. Hubble is not a GR guy. He's not going to solve Einstein's equations to figure out what the solutions actually mean. That's not his deal. He's an observationalist. And again, another hype up there. Here's the paper, a relation between distance and radial velocity, probably one of the most famous papers in all of astronomy. Proceedings of National Academy of Sciences. Such monumental works are not published so much there anymore. And again, he breaks it up in a similar way that Lemaitre did. 24 objects with an H naught of 465, and then if he groups them up into 9, he gets 513. The numbers are a little bit different because they use some little different samples. But the troubling thing at this point you can already see is if you just take 1 over the Hubble constant, let's forget corrections for lambda or things like that, you get a universe that's very young, 2 billion years old. And I told you, already in the early 1920s, we already know that the Earth is older than this. So already we've set up a conflict in the field. Okay, you say that this data is saying this, but we have other evidence, geological evidence, that we believe much more in, that says the universe is older than the Earth, or that the Earth is older than the universe. So how can that be? And this is a problem that's going to haunt astronomy, as us astronomers know, for a very long time. Here's the plot. Parsecs, distance, velocity. He uses kilometers. He doesn't use kilometers per second. I'm not sure why that is. Apparently, someone claimed that that was standard at the time, but I don't know. Here are the 2 different fits he used for the data for that 1929 paper. So Hubble, he looks great, right? He's discovered an external universe, and he's discovered the expansion of the universe. Okay, but Lemaitre keeps on going. He speculates in 1931 in a paper in Nature that the universe began as a primeval atom. So he realizes, well, the universe is expanding. It must have started from something. So he writes a paper and puts it down. That 27 paper is published in the same year. That paper with the Hubble constant, without the Hubble constant numbers in it. Origin this year, he reevaluates the Hubble constant from the data the best he can. He gets a lower number for the Hubble constant of around 290. That gets the universe up to about 3.3 gigayears. Not too bad, but still pretty close to the age of the Earth. And if you want to play with these numbers, I advise you to go to Ned Wright's webpage where you can play with this calculator and put all the kind of numbers you like. Okay, but things keep moving on. Richard Tolman, he shows in this fantastic book, which you can actually get on Google Books these days, that an expanding universe would cool and maintain its blackbody spectrum at some level. So he's saying, in this expanding universe model, this primeval atom model of Lemaitre,